Here you see in this slide, you see some points. You can easily identify 3 clusters, and graph-based learning algorithms. Essentially, the idea is that you build a graph on top of the data points, and you connect nodes if they are sufficiently close together, and you then connect them otherwise. And you can also put weights on these edges. So the more close the points are, the higher the weight should be. Okay, and then the idea is to use this geometric structure to try to detect the underlying geometry of the data set. So more precisely, in graph-based learning, one considers the similarity graph. So you have a bunch of data points, x1 up to xn, which sit in a very large space Rd. And you construct a graph, a weighted graph G, where the vertex set is given by the data points. And the adjacency matrix W is constructed as I was saying before, essentially. So you first impose that the diagonal is 0 because you don't want in the graph to have self loops. And then for points xi different from xj, you define the weight between point I and point xi and point xj to be a function of their Euclidean distance. I mean, this function could be also 0 at some point. So in that case, you don't have an edge. But when you have an edge, the principle is that the weight should be large whenever the distance is small. Okay, and so in particular, there are some choices of this function eta. Could be like an exponentially decaying function, or you can even take a characteristic function of an interval. In that case, you have an edge if the points are closer than 1, and you don't have an edge otherwise. Okay. So once you have defined the graph, you can define the graph Laplacian, which is nothing but a matrix. So the graph Laplacian, when you have n data points, is the identity matrix in Rn and minus 1 over n, and then you have d minus 1 w. So the w we introduced before is just the adjacency matrix. And now the d is the diagonal matrix of the degrees. And the degree of the node I is defined as the mean of the weights of edges entering into I. Okay, and then you take D to be the diagonal matrix, and then you can just invert it. And with this definition, del then is a non-negative self-adjoint operator with respect to this scalar product here. And this is the crucial object for many of the graph-based learning algorithms in the literature. So the general idea is that you want to use the graph structure to detect the underlying geometry of the data. And there are several examples. So for instance, label propagation, also known as Laplace learning. Then you have diffusion maps, P-Laplace learning, Poisson learning, and MBO. So we focus on MBO in this talk. And MBO stands for Merriman, Benz, and Osher, who actually introduced this scheme as a numerical scheme to approximate evolution by mean curvature flow. So it was not taught as a data clustering algorithm. But then Bertozzi and others revisited the scheme for data clustering. So let me introduce the MBO scheme. As I was saying, we want to perform data clustering. So we have a data set and we want to partition it into several classes. Now, the scheme that I have on the slides is the simplest setting, in which you want to split the data sets, the data set just in 2 clusters. You could actually write down the scheme for several classes, but for the sake of simplicity, just state the scheme for in the case where you have a data set and you want to split it in 2 parts. And for this reason, a clustering can be encoded as a function from the vertex set to either 0 or 1. So the values where the function is 0 is one cluster, and the points where the function is 1 is another cluster. So the algorithm works as follows. So you give yourself a step size h greater than 0, and you give yourself a proposed clustering, which comes maybe from another algorithm. Okay, you should think of it as of the MBO as a sort of refinement of your cluster. So you update your clustering by performing 2 steps. The first step is the diffusion step here, in which essentially so here this exponential is really the exponential of the matrix given by the graph Laplacian. So this is just the exponential of a matrix applied to the function chi, which is nothing but a vector. Okay, so here actually you are solving the heat equation on the graph at time h with initial value given by chi. And then in the second step, you consider each point in the vertex set, and you set the new update chi of x to be equal to 1 whenever x is in the super level set of the value 1/2 for this function that you just defined. Okay. So let's see one iteration. So here we have the 2 moons data set, in which, of course, I mean, the idea is that you would like to find an algorithm which is able to detect the 2 different moons. We start the algorithm with k-means. So this is obtained with k-means. And then in the first step, you see that there is a sort of diffusion where the values are like sort of the change continuously from values close to 0 to value close to 1. And then in the second step, you look at each point, and if the value is greater or equal than 1/2, you set it to be dark blue. Otherwise, you set it to be light blue. And you see that from here to here, you have already a great improvement in the accuracy of this clustering. And then, of course, now you could take this clustering here, feed it in the MBO scheme another time, and get another refinement. Okay?
What was the H you used in that picture?
Oh, I don't remember what H I used. It depends. I don't remember.
Yeah. So the question is how this depends on H.
Yeah, of
course. Is it pretty robust with H? Or?
No, actually, H is so H is very. The choice of H is the most delicate thing in this algorithm, because if H is too small, then you don't have enough diffusion so that nothing changes from one iteration to the other one. And on the other hand, if H is chosen too large, you go immediately to a trivial state in which everything is 0 or 1. But I mean, I don't remember what I used in this case here. Okay, and let me also mention that you could do sort of also a semi-supervised MBO, in which like you assume that some of the points in your data set are already labeled, and then you can if you have some information about some of the labeled points, you can construct a forcing term f from the vertex set to R, and to perform a semi-supervised learning, you could you can change the thresholding value by adding this term here. Now, if you see that, for instance, if x is a point which I know that has to have the value 1, then I could choose f to be very large so that this value becomes essentially negative, and this condition then is always satisfied so that the value 1 is enforced. Okay, so I mean, this is the basic idea to also include some information, prior information about known data points. Now, what we are interested in studying is the large data limit of this algorithm. So this is a sort of hot topic in theoretical data science, and the large data limit of an algorithm essentially is the following. So we want to study the behavior of the algorithm as the number of data points goes to infinity. Or in other words, we would like to understand whether the outcomes of an algorithm can be thought as approximating a continuum problem as the number of data points goes to infinity. This has been studied for spectral clustering, Lipschitz learning, Laplace learning, Poisson learning, and many other algorithms, especially graph-based. And this study, of course, is academic, but also sometimes it gives insights on parameters tuning, regimes of validity of an algorithm, and also maybe design of new algorithms. So the framework to study large data limits is the following. So of course you have to put yourself into a mathematical framework in which this question makes sense. Okay. So what we assume about the data is that the data satisfies the manifold assumption. In other words, so also in practice, when you have a data set, maybe you have tons of features, but many of them are correlated to each other. So actually the true dimensionality of the data set is lower than actually the dimension of the feature space. So what we assume is that we are given data points xi, with I from 1 to infinity, such that they lay on closed k-dimensional Riemannian submanifold of your feature space, and the points are IID, and they are distributed according to a probability distribution on the manifold, where the probability distribution is absolutely continuous with respect to the volume form with a sufficiently smooth density. So once you have this, you construct a sequence of graphs, Gn, where the vertex set of the nth graph is just a collection of the first n data points. And then the adjacency matrix Wn is constructed as before. So we put we take for points xi and xj, we put the weight to be a function of their Euclidean distance. Just that now you also rescale by a parameter epsilon n, which will go to 0 as the number of data points goes to infinity. And this is done because if you were not to rescale in this way, then in the limit you would have a totally connected graph, and so you would lose the local information. Okay, and and on the other hand, you have to have that epsilon n is sufficiently large compared to the number of data points, because otherwise the graph becomes disconnected, and then I mean that's also a problem. So you rescale the weights in this way here, and you rescale also the graph Laplacian by epsilon n squared, so that this is known in the literature. You have a convergence to a continuum Laplacian. This continuum Laplacian here is defined as follows. So for a function f, this is just the weighted Laplacian with weight rho squared. Okay, this constant here depends on the function that you choose eta, but you can think of it as being one. It's not important. Okay, this is the sequence of graph we are considering. And then on each of these graphs, Gn, the algorithm, the MBO scheme, generates a sequence of clusterings, right? Because let's say I fix h, the step size, I fix n, so the nth graph, and I feed into the nth graph the clustering chi0 hn. Then I perform MBO and I obtain a clustering chi1 hn, which can be fed into MBO again, and you obtain another clustering and so on. So you have a sequence of clusterings for each graph, okay? So in the literature, usually, I mean, in application actually, in applications, you take your final clustering to be one for which you have run enough iterations. So you fix a very large L, the number of iterations, and you end up with the final outcome of the scheme, okay? So we are interested, when we want to study the large data limit, we were interested in understanding what is the asymptotic behavior of this final outcome as the number of data points goes to infinity. That's the first question we want to answer. And then we'll see that actually the choice of this final outcome actually depends on the whole dynamics. So we will be interested also in studying the limit of the whole dynamics of the algorithm. So not of the just of the final step. Okay. So let me talk first about this first question here. So a fundamental observation of about the MBO scheme is due by Ezedoglu and Otto, and says the following. So when you are on the nth graph and you are on in iteration L, you want to obtain the new clustering. You can perform the two things we were doing before. So we can do diffusion and thresholding, which is the definition of the MBO scheme. But actually, the observation is that this is equivalent to solving this variational problem here. So to obtain the new clustering, you solve this minimization problem here, where this energy here is called the thresholding energy. And this is a distance term corresponding to this minimizing movement scheme here. Now, the explicit form of this distance term here is not too important right now, but the thresholding energy is defined here. So for a function u from the vertex set to the interval 0, 1, the thresholding energy is defined as the inner product on the graph between 1 minus u and the diffusion of u through the heat kernel at time h. So this is nothing but essentially the heat content on the graph. Okay, because in the case when u is actually a characteristic function. So this observation tells us that if I perform enough iterations, I will be close to a local minimizer of this energy here, right? So the idea is that if I want to study the asymptotic behavior of the final outcome of the MBO scheme, I can just look at the convergence of the minimizers of that energy, which is nothing but the gamma convergence of these energies here. So I will have a slide now about gamma convergence. So essentially, I mean, the outcomes of MBO scheme are local minimizers, and I want to have a notion of convergence that ensures convergence of local minimizers, okay? And this is exactly gamma convergence. So I have this slide. So if you are on a metric space, and you have a sequence of functions fn and a function f from the metric space to R, if you want to a notion of convergence that ensures that the minimizers in this sequence converge to minimizers of the limit, then the right notion of convergence is gamma convergence. Gamma convergence says that it is a definition that exactly ensures this. I have the definition here. If you have seen it before, you recognize it. If you don't, just believe it. But the definition is as follows. So we say that f is the gamma limit of sequence fn if for every point in the metric space and every sequence converging to this point, it holds that this limit inequality holds. This is for every convergent sequence. And then the second requirement is that for every point, there exists a sequence such that the reverse inequality essentially holds. Okay, so this lower bound here is sharp. I mean, it's a fact that gamma convergence implies the convergence of minimizers. So this is really the notion of convergence that we want to use to study the MBO scheme. So, and the result that we have for this is the following. So let's assume that we are in the regime, in this regime here for the epsilon n. So epsilon n is large enough compared to the number of data points. And we show that it holds almost surely that as the number of data points goes to infinity, the thresholding energies on the graph, they gamma converge with respect to the weak TL2 topology to the energy EH defined here. So let me pause. I mean, we'll see in a moment what this weak TL2 means, but let's look at the limiting energy. The limiting energy is the heat content on the manifold. You see here, we have an integral on the manifold with respect to the measure rho squared volume form, and here we are integrating 1 minus u and the diffusion of u through the heat operator associated to the continuum Laplacian that we have seen before. Okay, so this is nothing but the heat content on the manifold. So we are saying essentially that as the number of data points go to infinity, the outcomes of the MBO scheme will be close to local minimizers of this energy here. And then, let me just pause for a moment to say what this TL2 convergent is. So we are studying the gamma convergence of energies defined on graphs to an energy which is defined in the continuum. And this requires us to have a notion of convergence to compare functions defined on discrete data points to functions defined on the manifold, but which are just L2. So in particular, I cannot consider just the restriction of a function to the data points because this is not well defined. So what we use is a notion of convergence introduced by Garcia-Trillos and Slepchev, which says that a sequence of functions un converges to u in TL2m if and only if two things hold. So the first thing is that there must exist a sequence of transportation maps between the probability measure nu and the empirical distributions of the first m data points, such that this limit holds true. And then it must be true that the composition of UN with these transport maps converge to U in L2 on the manifold. In particular, essentially, what I'm saying here is that the measures UN must converge to nu in the Wasserstein sense, plus you have to have this L2 convergence here. And for us, the notion is not TL2 convergence, but weak TL2 convergence, but it is just a modification in which you say that everything converges in weak TL2 if this convergence here is weak in L2. So it's not a big difference. Yeah, so the first result tells us something about the convergence of the MBO scheme in the continuum as the number of data points goes to infinity. But we still have the step size. The step size is still fixed in the continuum. So what we do is we also understand what happens as the step size goes to 0. Now we are just in the pure continuum case. So we study the convergence of the heat content on the manifold as the step size h goes to 0. And we show that with respect to the strong L1 convergence, you have that these heat content energies converge to the weighted area functional. The weighted area functional is defined as the integral. So for a function, let's say if chi is the characteristic function of a set omega, the energy E is nothing but the integral on the boundary of omega of the density squared. Okay, so this result is more like a classical analysis, but actually it's interesting that this was not true. Was not known before. It was known only in the flat case. But if you go in the curved case, as in this, as we are doing, so here we are on a manifold, the result is not just a straightforward generalization of work done before. So this is also interesting in its own. So for this first question, so the convergence of the final outcome of the scheme as the number of data points goes to infinity, we could actually take actually the MBO scheme to be the multi-class MBO. So I presented just the case in which you have two classes, but whatever I said works in the multi-class case. We can also extend this analysis when you do this semi-supervised MBO scheme, because in that case, the energy that is used in the minimizing movement is just the thresholding energy plus this term here, which is linear. And so the gamma convergence still holds true. And then you can also include other variants of graph Laplacians and data-dependent weights. The main problem that we don't solve is this. So here, what we said is the thresholding energies, or in other words, the final outcome of the MBO scheme converge as the number of data points to go to infinity to local minimizers of the thresholding energy. And then we say, then if we let h go to 0, we converge to minimal surfaces. So in a certain sense, as the number of data points goes to infinity and then the step size goes to 0, we have that the final outcomes of the MBO scheme are close to minimal surfaces. The problem is that these limits are taken disjointly. What we would like to do is, we would like to understand is what happens to these energies when you consider, let's say, a sequence of step size hn converging to 0 as the number of data points goes to infinity. So you would like to have this sort of diagonal error. This is interesting because this is related to the thing that we were mentioning before. So if h is too small, the algorithm is pinned, and if h is too large, then the algorithm is trivial. So actually, to have this, you have to have a sort of relationship between h and epsilon n, and that's what we conjecture to be true. But we are not able to show this now. Okay, so this concludes sort of the story for the first question. So convergence of the final outcome. Now for the dynamics, let me mention again what we mean. So we have seen that if we consider successive iterations of the MBO scheme on each graph, then the final outcome is close to a local minimizer of the thresholding energy. But this, as always, the selection of local minimizers depends on the dynamics that you use to go to the minimizer, as you do also for neural networks. I mean, initialization of a neural network is an important variable, right? So we want to understand what happens to the limit. Let's say we consider the whole dynamics on the nth graph, and then we let the number of data points to go to infinity. We would like to understand what happens in the continuum for this evolution. Okay. Now, this is interesting because as I was saying before, if the step size is too small, the scheme gets pinned, and if the step size is too large, the scheme becomes trivial. And so we study the convergence of these dynamics in the two-class case. So we focus now really on the case in which the MBO scheme partition the data set just in two classes, because the idea is that we will use viscosity solution techniques, which are available only in this two-class case. So let me just briefly tell you what happens. So the spoiler is that the dynamics of the MBO scheme will converge to a viscosity solution to mean curvature flow on the manifold. Okay, this is the spoiler. I will tell you later how it works. But if you believe this, let me introduce mean curvature flow on a weighted manifold. So mean curvature flow on a weighted manifold is nothing but the trajectory of steepest descent for the weighted area function. Okay, and if you write down the PD, this is reads as follows. So you have an initial set omega 0 on the manifold, and then mean curvature flow is nothing but the evolution of this set, so that on the boundary of the set omega t, the normal velocity is equal to minus the mean curvature minus the inner product of the outer normal with this gradient here. So if you observe this PDE, you see that this PDE is driven by minimizing area by the mean curvature and density by this term here. So if you believe that the MBO scheme will have as a limit this PDE, this makes a lot of sense for the scheme to be effective, because it says that the dynamics of the MBO scheme is sort of driven by minimizing the sort of graph cut and the density, which is exactly what you would like in a clustering algorithm. So just a brief comparison with what is known in the literature. So the convergence of the MBO scheme in the classical Euclidean setting is was studied by Bars and Georgelin in this viscosity solution setting in '95, and then the only result for the graph MBO scheme is by Mitzes and Yip in 2016, but just on regular grids. So their graph is just a discretization space. They do this to study actually the classical MBO scheme, to see how the numerical algorithm for the convergence for the approximation of mean curvature flow works. But in this graph clustering setting, nothing was known before. So here what we do, we extend these ideas and say that, and we're able to say that on random graphs, the MBO scheme will converge to manifold mean curvature flow. So let me just briefly explain to you how why this is true, or why this is true. So now I restate, I rewrite the algorithm in an abstract form. So the algorithm is exactly as before. The only thing that I changed is here, where instead of the hit operator, I introduce this abstract notation in which I use SNHN, where SN is an abstract operator on the graph. Okay, so you can think of it as a semigroup, but it does not have to be a semigroup. In the classical case, is the Euclidean, is the graph fit curve. So what we prove is that if the sequence of operators Sn are close enough to the continuum hit kernel, then the MBO scheme converges to the manifold mean curvature flow. And this is true with whichever sequence of point clouds you take. So in particular, you don't have to have a graph structure for this result to be true. So there will be some conditions that specify this Sn being close enough to the continuum heat kernel. But if these conditions are satisfied, then you have convergence of the MBO scheme to manifold mean curvature flow. And then the second step is we prove the following thing. We prove that on random geometric graphs, you have with these two choices, and comment in a moment with them with these two choices, this condition here that we see in the first step is satisfied with very high probability. And in particular, this implies that on random geometric graphs, MBO scheme converges to manifold mean curvature. The operator that are allowed in our analysis on random geometric graphs are, of course, the full heat kernel on the graph, which is what we have seen up to now. But most interestingly is this one, because so in applications you don't compute the full heat kernel. That's too expensive if you want to run this algorithm. What you usually do, you just take the first k eigenvectors of the graph Laplacian, and you approximate the heat kernel using these first k eigenvectors. And we show that also in this case, this result is true. So let me just finish. Let me just go a bit more in detail about what I mean by these two steps. So the first step is this one. So when I say Sn has to be close enough to the manifold heat kernel, I mean these three conditions. The first condition says that the operator Sn should satisfy the comparison principle up to an error of order h to the 3/2. Then you have to have consistency result, which says that whenever you apply the operator Sn to smooth functions on the manifold and you compare them with the heat kernel on the manifold applied to these functions f, you have to have these sort of estimates here. And then the last thing is more technical. It's just you have that Sn must preserve constants up to this order error of order h to the 3/2. So if these three conditions are satisfied, then you have convergence of the MBO scheme to mean curvature flow. And then on random, when you consider random geometric graphs, you have that if you choose either the graph the graph heat kernel or a truncated version of the graph heat kernel, then the previous conditions are satisfied with with expression, so with very high probability, provided these three conditions hold true. So the fourth condition is just technical. It says essentially that the eigenvalues of the limit have to be simple, but it's just a technical assumption. But what is the most interesting assumption here is this one. So you want the number of eigenvectors that you use to approximate a heat kernel on the graph to be just greater or equal than the logarithm of n, essentially, to the power q, which is an exponent which comes out in the proof. But as you see, I mean, the logarithm of n is a very small number compared to the number of data points. So this result is really interesting for applications because it says essentially that what has been done up to now by practitioners makes sense, because in the limit you recover still a meaningful PD. And in fact, I mean, yeah, let me finish on this. So there are other two conditions. The first one is about the step size. So the step size has to be large enough compared to n. And this makes sense because, as I was saying before, if the step size is too small, you would get pinned, and the algorithm would not work. And then this is assumption here on epsilon n. The lower bound is the standard is part of the standard assumption on the connectivity rate, and the upper bound is more a technical assumption. And the corollary of this result is that on random geometric graphs, under the previous assumptions, graph MBO scheme converges to manifold mean curvature flow. yeah, this gives insight on the number of eigenvectors or eigenvalues that you use to approximate a heat kernel, and also on the choice of the step size h. And the main technical ingredient that I want to talk about for the proof of this result is a new heat kernel estimate, which is interesting on its own, and which extends a work of Danson, Wu, and Wu from 21, and is as follows. So when I'm talking about the operators obtained by truncating the heat kernel on the graph, I'm talking about the following thing. So here I consider psi in to be the eigenvector on the nth graph, the eigenvector on the nth graph, and lambda in to be the corresponding eigenvalue. So this operator here can be rewritten in the following form. So this is nothing but the heat kernel on the graph obtained by truncating the frequencies higher than Kn. Okay. So the result that is the main technical result of our paper says that in the previous in the setting of the previous theorem, you have that if you compare this operator here that I just introduced to the heat kernel on the manifold, this is the heat kernel on the manifold, and you take the max over points xy on the nth graph, then this error estimates holds true with very high probability. And this estimate is interesting in its own because, I mean, it could also serve as a sort of theoretical result to sort of approximate the short time behavior of the heat kernel on a manifold. So if I give you a manifold and you say you would like to approximate the heat kernel for short times, you could like sample points on the manifold, construct the corresponding geometric graph, and use this construction here to approximate the heat kernel. And the crucial ingredient for the proof of this result I want to mention is that is the L infinity convergence rates for eigenvector of the graph Laplacian. This is a result of Calder, Garcia-Trillo, and Levicka from 22. And this is really a crucial ingredient for the proof. Now to conclude, and then maybe we have time for some questions, I just want to make a summary. So we have seen that the outcomes of several iterations of the MBO scheme are close to local minimizers of the graph thresholding energies. And we have proven that these local minimizers are qualitatively close to minimal surfaces on the manifold. Then we have seen that the selection of local minimizers depends on the dynamics of the MBO scheme, and thus we studied the dynamics of the MBO scheme, proving that it converges to mean curvature flow in the viscosity sense. And some future work we have to address is, of course, we would like to study this the joint gamma convergence of the thresholding energy that I was talking about before, because this would allow us also to study the convergence of the dynamics in the multiclass case. And as I was saying here, because if you have convergence of the energies, then you could use other notion of solutions for mean curvature flow, like Brachy solution or the Georgi solution, which are available in the multiclass case. And then we would also like to maybe test a bit more the parameter regimes numerically, so that we could avoid a bit of parameter tuning when you use the algorithm. That's why we are thinking about extending this result to the setting of k-nearest neighborhood graphs and not epsilon geometric graphs as we constructed here. Okay, let me just finish by saying that so you find these two works on the archive. I mean, we submitted them, but takes a bit of time, but there is a report which summarizes these two works if you're interested. The PAM report is like 3 pages long, so it's very short. So I would like to thank you for your attention, and if you have questions, I'm happy to take them.
Thank you for the talk, and if you have a question, raise your hand, and then also from Zoom, if you have questions, just type in the chat.
I have an extremely naive question, sorry. So mean curvature flow in the continuous setting can easily develop singularities or even situations where it's not uniquely continuable.
Yes.
How do you see that in your result, right? Because I imagine the MBO scheme, like singularities don't make a lot of sense in a discrete world, and like presumably you can always uniquely continue it. So is the gamma limit like picking one of the branches, or like skipping over the singularities? Maybe there's something that I was not seeing completely.
So I mean, the MBO scheme goes through singularities also in the continuum case. So you can go through singularities because I mean it depends. I mean, if, for instance, one of the classical examples of non-uniqueness, also in the multi-phase case, is when you have the cross. You have the cross, you don't know how to continue it. But the point is that depending on how you implement the MBO scheme, you will give preference to one of the phases, and then you will be able to choose one continuation. Will not be stuck. Now, in terms of the energies, you have the gamma convergence of the energies, so you'll be able always to say that the local minimizers converge to a local minimizers of the limit. The local minimizer of the limit in that case could be the cross itself, but that's not a problem for this result, because you're just saying that maybe you converge to a minimizer which is unstable, but it's not a big deal.
That's a question.
Yeah.
So I think gamma limit only guarantees the convergence of global minimizers.
Well, there is also under suitable assumptions. There is also a result of Kohn and I don't remember the other author that ensures convergence of local minimizers.
So
if they are isolated local minimizers.
What's the global minimizers or local minimizers?
No, global minimizers in this case are just trivial minimizers. Actually, this is a good point, because I mean, if I were to talk about gamma convergence and only global minimizers would be analyzed, in this case would be trivial, because the global minimizers of the thresholding energies are always trivial minimizers, so function 0 or function 1. But two remarks. First is the first remark is that the gamma convergence also ensures convergence of local minimizers in this case. It's a bit technical to see, but one can show this. And then the second remark is that if you use the MBO scheme in the semi-supervised setting, which is this one, which have also this forcing term, then the energy is thresholding energy minus the linear term of F multiplied by chi. And in that case, also global minimizers are not trivial anymore. So you still have information. So this it's good that you pointed out, but yeah, there are these two observations that actually makes it have sense.
You also have a question in the chat.
Nice to, a lot of your estimates are quantitative. Is there any hope of getting a quantitative convergence rate in addition to gamma convergence? You mean for the first, so for the second result, yeah, for the second result, I think we should be able to get convergence rates. For the first result, well, for the first result, it would be nice, because if you would have quantitative convergence rates for either the first limit or the second limit, actually you would be able to use these quantitative convergence rates to actually prove something about the joint limit, the diagonal limit. But for the moment, everything is just qualitative, because for instance, the main point why everything is qualitative. So the second limit, so h to 0, I don't think you can do it quantitatively. The first limit, n to infinity, maybe you can do it quantitative, because in that case what we use is actually we prove the convergence of the heat operator using just the energy dissipation inequality for each, which is true for every gradient flow. So the argument is very soft, let's say. Maybe if we use the heat kernel estimates that we proved in this second work, maybe we would be able to actually go back to the first work and prove something quantitatively, but I'm not totally sure that this can be done, because the problem is that the heat kernel estimates that we have in this second work, they are true. The problem is that you would like to apply in the first result, you would like to apply the graph heat kernel to functions which do not come from the restriction with of a smooth function on the manifold. So I don't know if this will help or not. I don't know if this answers your question. Yeah, okay.
So in one of your slides on the dynamics, you had a comment that your analysis can help you choose or determine the constant, Hn, and also the number of eigenvalues. Do you use it in practice?
I mean, what I mean here is that gives sort of insight what number of eigenvalues are allowed in practice. So in practice, people were always taking some logarithm of n. So that matches what people were doing in the literature. Now, for the choice of the step size, usually people go by trial and error. They have a data set, they try a bunch of values, and they see what is the best one. Now, in our case, we have this, we say that Hn must be larger than this value here. And we would hope that maybe choosing H in this regime would always work. That's the utopic goal. But the problem is that if you want to test this numerically, so this result is described in a setting where you have epsilon neighborhood graphs. Okay, so the problem is that this H larger than this quantity here is related to the fact that epsilon must be larger than this and more than this. And but in practice, you never use epsilon neighborhood graphs. So that's why I was saying what we should do is to extend this result to k-nearest neighborhood graphs, because in that case you would get maybe something different on H, but you know exactly how to construct the graph in the proper way. Because otherwise, you have when you want to apply this in practice, you would have to choose epsilon, which is I mean, it's not possible, because the epsilon must be adaptive compared to where you are on the graph. And that's exactly what happens when you use k-nearest neighborhood graphs. You have a self-adapting, essentially, localization parameter.
Thanks.
I have a question.
Yeah.
For your semi-supervised algorithm,
yeah,
when you introduce the drift term,
yeah,
then do you know what is the optimal choice for this function?
No, no. So this is a bit problematic in this case, because what we show is that so if you want to use this f here, in practice, to have a consistency in the limit, you would have to use a sequence of Fn which converge in TL2 to a limit F. So in particular, for instance, you cannot simply take like a function which is localized on a finite set of points. Usually, I mean, when people do this analysis of semi-supervised algorithms, they like to take a fixed number of known data points, and then you take the other number of data points to infinity. This would not work in this case because, of course, this would have TL2 limit 0 in the limit. So what you can do is first you take your label data points, then you propagate these labels with another graph-based learning algorithm, and then you use the sequence that you obtain, the sequence of functions that you obtain to in this setting. For instance, in the paper we wrote something about Lipschitz learning, because Lipschitz learning has a limit in TL2, but you have to be careful with Lipschitz learning, because if you don't redefine the weights in a data dependent way, you don't you lose the information about the density in the limit. So this would not be very meaningful. But yeah.
Okay, any other question? All right, thanks Jona for this nice talk.